Okay, YouTube, in this video we're going to solve some quadratic equations that are conveniently solved using square roots. That is, typically when we deal with quadratic equations, especially in standard form, we have things of the form y equals ax squared plus bx plus c. But sometimes we're dealing with equations in which our bx term, or at least our b coefficient, is 0, and therefore we're only dealing with an ax squared and some constant c. As you can see in these two examples right here, example 1 on the left and example 2 over here on the right. So when this is the case, we can actually solve these using square roots. So our method of operation here, our modus operandi, is going to be to isolate, that is, isolate the squared thing. Okay, so like for example, on the equation on the left over here, we have 2x squared plus 1 equals 17. We're going to get x squared by itself, and on the equation on the right here where it says 3 minus 5x squared is equal to negative 9, we'll get this x squared by itself. And the reason why is because once we get that isolated, we can undo the squared with the square root. So let's go ahead and get started, take a look at these, and we're actually going to look at these graphically as well. But we'd say, okay, so 2x squared plus 1 equals 17. If we want to isolate the x squared, we'll go ahead and subtract 1 from both sides. So subtracting 1 from both sides of this equation, we end up with 2x squared is equal to 16. Furthermore, 2 times x squared, we want to get rid of multiply by 2, so we'll divide by 2. We get x squared is equal to 8. So now we say, all right, so now that I've got the squared thing isolated, we can take the square root of this x squared here. Now recall, square root means what could you take times itself to get this thing? And I'm saying, okay, well, what could I take times itself to get x squared? Well, x, okay, so we say x. So x equals plus or minus radical 8. Remember, the square root of a positive number, if you watched my last video, square root of a positive number has two roots, the positive root and the negative root. So now, this is very, very good. This is the answer. I mean, we can plug this back in and check it. That wouldn't be hard to do. As a matter of fact, let's go ahead and do that now. We say 2 times blank squared plus 1 equals 17. If we were to throw now our plus or minus radical 8 back in here, you'd notice that the plus or minus, it's not going to matter because when we square it, we're taking that times itself, and a positive times a positive is a positive. And a negative times a negative is a positive, but when we square root of 8, the squared and the square root, they cancel out, and we get left with this. 2 times now just 8 plus 1 equals 17, which of course is very, very true, because 16 plus 1 is 17, and 17 is indeed 17, okay? So this is the solution, or these are the solutions. But furthermore, what we can say is this is not in simplified form, in simplest form. The reason why is because, well, we can think of a perfect square that goes into 8, 4 does. So it's the same thing as square root of 4 times 2, and again, if you watched my last video, that's the same thing as the square root of 4 times the square root of 2, and the square root of 4, of course, is 2. So we'll say, well, the square root of 4 is 2, we'll go ahead and put that 2 out front. So our solution here is plus or minus 2 radical 2. So now I want to pick on this. A couple things I want to do with it. First of all, I want to type it into a calculator. So 2 times radical 2, we say 2 radical 2. We end up with, let's take a look. 2 radical 2 is about 2.828. So 2.828, roughly speaking. So we say in this case, x is approximately plus or minus 2.828. Now, if we would like to interpret this graphically, I'll take your eyes back up to the original equation here. Actually, we'll just relist it down here. 2x squared plus 1 equals 17. So now, a method that we typically learn before solving using square roots is factoring. And so if we're going to solve this by factoring, what we do is we often set it equal to 0 first. So just to show you here, if I were to actually subtract 17 from the left and right hand side, we get 2x squared minus 16 constants equal to 0. So now, what this is really kind of like saying is this. We're saying, all right, well, this is some expression here, and this is kind of like saying, well, y equals 2x squared minus 16, except for we're letting y be equal to 0. And when you allow y to be equal to 0, okay, we're saying if y equals 0, we get 2.82-ish when y is 0. We also got negative 2.82-ish when y was 0. But what this does is it gives us a couple of ordered pairs. So taking a look at this graph, okay, let's take a look here. We said y equals 2x squared, and this is minus 16. So here's our parabola. I know it's kind of hard to see here. There it is. The vertex is way down there at negative 16, but you'll notice something here. We say, well, when y is 0, what are our x values? And really what we're indicating is this. We're saying, okay, what are our x-intercepts here? Here and here. Because when y is equal to 0, we're saying, well, we're on the x-axis because these are the points, x values for which our graph had a height of 0. And you'll notice up here on the left, we say, well, negative 2.83-ish and 2.83-ish. But when you're solving a quadratic equation, what you really are finding, you're finding the x-intercepts. Okay, so these are the x-intercepts here, this plus or minus 2.828 when you solve this equation. So let's go up here and let's take a look at this second example. Again, you'll notice that there's just an x squared. There's no x to the first. So we can go ahead and isolate this x squared. So let's start working on this. We say minus 3. We'll take away 3 from both sides. So we get negative 5x squared is equal to negative 9, take away 3 more is negative 12. So now moving right along, we say, okay, well, we need to divide by negative 5 to get this x squared by itself, divide by negative 5. So we end up now with x squared being equal to positive 12 fifths. Now, to undo the squared, again, since we've isolated the squared thing, we're going to go ahead and take the square root of it, and that's going to undo the squared. So we get just x now, and now x equals square root of 12 fifths. Now, recall that this is the same thing as the square root of 12 over the square root of 5. So a couple things we have to deal with here. First, the first thing we need to deal with is this. I can think of a perfect square that goes into 12. That is, I can understand, or I know that 12 is the same thing as 4 times 3. And then we have over radical 5. And so I mentioned this because the square root of 4 is 2. So we're going to put that plus or minus 2 out front. And so now we have this expression. We say plus or minus 2 radical 3 on top, all over radical 5. Now the other problem we have here is this. We've got a radical in the basement, in the denominator, and we don't want to have that. We want to rationalize, okay? That's the key word, that we want to rationalize our denominator. And rationalizing the denominator is done this way. We say, okay, so, well, I can get rid of the square root of 5 by squaring it, but I can't just square the top and bottom of a fraction. So our method's going to be this. We'll square it, all right. We'll take it times itself, but we also have to take the top times radical 5. So what we end up with is this. On the bottom, radical 5 times radical 5 is really radical 5 times itself, radical 5 squared. And that just leaves us with 5. And on top we have this, plus or minus 2. So that plus or minus 2 is still there. Then we had radical 3 times radical 5. But recall that the property of products with radicals says this. A radical 3 times radical 5 is radical 3 times 5, or just radical 15. So we say our two roots in this instance are plus or minus 2 radical 15 over 5, or positive radical 2 times radical, or excuse me, let me slow down a second here. The two roots are 2 radical 15 over 5, and then the other root is negative 2 radical 15 over 5. Okay, so we end up with two roots. So got to use those properties of quotients and products and have to rationalize denominators from time to time, but recall that you always get two roots, and solving using square roots is convenient when you have just a squared term and no, say, x to the first term.